Good morning. I hope you're doing well. I just had a bit of a panic. The reason the stream was a couple minutes late is because when I went to start the stream in OBS, it just was like, oh, there's an error. I can't connect to your YouTube account. I'm like, shit. Thankfully, just disconnecting OBS and then reconnecting it magically worked. But we'll see. There's a couple things there's a lot of things going on in today's stream. There's a lot of stuff connected to my computer right now, and I suspect that might have been why there could have been a problem. So hopefully none of those links have broken and we get a nice smooth experience today. We'll find out how we go. Howdy, Prop Guru. All right. Yes. So I don't have a normal PowerPoint this week because it's kind of disjointed, and I don't know. I honestly didn't really have enough time to like flesh out the PowerPoint to make it all nice and clean. And we're going to be swapping between screens a lot anyway. So it's mostly just going to be different camera views. It's going to be cool. Prop Guru asks, did you play around with the opposing magnets for the thrower? I have not. I have some things to mention about that. I want to save that for a little bit though. Yep. Yeah, that's the quick answer is that's not really going to be a concern for a little while. So I haven't touched that yet. I've got a couple other more pressing things to worry about for now. Yeah, but I definitely have a lot to say about that. Yep. Okay, the very first thing that I want to mention is we have another... the only thing that I do have a slide for... Oh, it's not worth opening up PowerPoint properly for it, is this week's fun tangential thought, which is the idea of using Jugglebot to bounce juggle and play the piano at the same time. So bounce juggling is something that you may not have heard of. It's not really a super common type of juggling, but it's used a little bit in performances and that sort of thing. The general idea is you have like super bouncy balls. Like I have some that I believe the coefficient of restitution is like how high they bounce from how high you drop them is like quite a bit over 90%. It's something like 95%. So if you go on like a really hard concrete surface and you drop it from a meter high, it'll bounce to like 95 centimeters or so. They are ridiculous. It does mean, because they're so bouncy, I personally don't really like doing it because they're so bouncy, so whenever they collide, they just go everywhere, and it's just such a hassle to practice. But you can do some very, very cool things with it. Like this video here, where we have the world's fastest piano juggler, part 2. And I've put a link in the description for this, and the audio won't be playing now, so you won't be able to hear it. But you can probably get the idea. I'll play the audio for you, so... Oh, no, alright, never mind. I need to set things up to make that work. But you can watch this video yourself. There's a link in the description and you can check it out. But you get the idea. Like you throw balls at the piano and it plays the notes. So there are 2 songs in particular that I think would be particular that like made me think about this. And these are Said and Done by Nils Frahm. There's been a couple of Nils Frahm's songs that I've brought up, and I'm a big fan of his work. And also Hania Rani is also a very, very good pianist, and I really like the song. I think Now Run would work really well. I think whenever there's like repetition of notes that is nearby each other, I think that works really well for this bounce juggling. Now, one thing you may notice is that when this guy is doing his bounce juggling, he's actually throwing the balls down. And there's actually 2... As far as I'm aware, I'm not a professional bounce juggler or anything, but as far as I'm aware, there's 2 main ways to do bounce juggling. One of them is like this, where you throw down and then the ball goes down, bounces off the piano in this case, comes up, peaks, and then you catch it after the peak. That, I think, would be very difficult for Jugglebot to do because they would need to be able to orient his hand from the catch here to the throw here, which for humans is very easy to do. Our wrists are very, very mobile. But for Jugglebot, especially in its current form, ain't no way that's flipping around. So that's not going to happen. But there's another way to do it where you can basically throw and catch upright. So you do like a very, very small throw out the top of the hand. That goes down, bounces off the piano, and then you again catch it after it's peaked. So that sort of bounce juggling should be doable with Jugglebot. Of course, this is going to require a lot of... it would need to be very precise for this to work, but it would be pretty damn cool. And Prop Guru says, I'm friends with Fast Wally, aka Wally Eastwood. Is that this guy? It's been a little... No, this is Dan Menendez. Fast volley rings a bell though. I did a little bit of looking into bounce juggling stuff a couple of years ago, but I haven't really looked at it since then. But that's cool that you know him. Prop Guru also says it would need to catch on the up. I don't think so. I think throwing with a small peak, bouncing, and then catching after the next small peak should work. Of course, the second small peak is going to be slightly lower than the first one because things don't bounce to the exact same height. But as I said before, the coefficient of restitution for balls that you use for this is super high, so they get it up to pretty much the exact same height. So I think it should be possible. And yeah, I think that'd be really cool. That would be very, very cool. Especially like there's just so many things that you can't do with a human because you just can't be in like 5 places at once. But like playing like Rush E, maybe with the Jugglebot piano playing would be pretty cool. It's like if you use like the 3D aspects, so you can kind of like juggle out of the plane of the piano. I don't know. Lots of things to think about here, but it's very cool. Yeah. Yeah. All right. So now let's get into what I have done from last week. So there's been a lot, and there's a lot of... I've kind of worked on like several different aspects of this stuff, so figuring out a good way to present this so there's like a clear through line that will hopefully make a bit of sense to you guys was a little bit tricky, but hopefully this makes sense. So the first thing I want to touch on, and this is not in chronological order with how I did things as well, this is just how I think will make the most sense for you. Hopefully. We'll see. Yeah, the first thing I want to go through is that I have had success with testing the motors. So you may remember that I am planning on using one ODrive 3.6, which is what this is, to control... This is for... Let me step back a bit. Making ball butler to throw the balls off of that shelf up there down to Jugglebot. I'll show you the CAD as a reminder. You may notice some different things already, but I'll talk about that actually. Let's go to this one. This is more similar. It's a bit messy, work in progress, but we're getting there. So the general idea is that there is this guy, that like the hand part that can throw the ball. So this thing can go up and down. I don't know, Onshape likes to move the wrong thing, but this cup part can move up and down that rail. This guy can move up and down on that big arc, on the big red arc. And then on the base, the thing that's causing all the problems with the mating right now, this can also spin around. So this will be able to basically throw to anywhere where I want it to. You can orient and then throw. Yeah, so I'm planning on using an ODrive 3.6 to control this motor and this motor. So one single controller will control the orienting of this robot. And then the last motor, the third motor that does the actual throwing, will be controlled by the ODrive Pro. The reason why I have I've made these choices, which is a big topic of discussion for today. A big reason why I've chosen that is because there's 3 motors, so I can't use 2. It doesn't really make sense. It doesn't really make sense to use 2 ODrive 3.6s because then there's like a free axis that's just kind of wasted. Also, the hand needs to be controlled very precisely. It's definitely not as sensitive to how precisely it's controlled as the actual Jugglebot hand, because we don't need to be doing any catching here, we just need to throw. So it's possible that the ODrive 3.6 would be completely fine with this, but the ODrive Pro is just more performant. It's faster, it's better. It's more modern. I mean, then the ODrive people are not recommending that you use the ODrive 3.6 for anything new anymore, and I'm not going to buy anymore, but I already have 4, so I kind of want to use them for something, and they're not doing anything right now. They're just sitting in boxes basically. Yeah, so I want the ODrive Pro for the hand because that has like the most sensitive control. But then the other 2, it's like I could use 2 ODrive Pros. I do have 3 ODrive Pros spare, but only 3. Jugglebot, I bought 10 originally. Jugglebot is using 7 of them. And so I have 3 extra, but I'm really hesitant to use those 3 because it's possible that I want to use them in the future, and it feels a bit overkill for using like $600 of motor controllers for this thing when, yeah, it feels a little bit unnecessary, especially when I've got the ODrive 3.6s just kind of sitting around. So yeah, I wanted to use the ODrive 3.6 to control these 2 motors, the pitch and the yaw. But it's been a little while since I've used these controllers, and you may remember that a big part of what I want to do here is I want this system to not require any homing stuff on startup. I want to just be able to put the power in, which I want to talk about later today as well. I've got a bit of a better idea of the circuit wiring diagram and everything, so stay tuned for that. It's not fleshed out yet though, so there's some details missing. But yeah, where was I going with that? I don't remember. Yeah, actually no, sorry. So I didn't want any homing stuff to happen. I wanted to just be able to put the power in and then have it be ready to go. Have it know exactly where it is and be ready. Because otherwise it's like you got to introduce limit switches or some kind of like homing sequence where it detects the current spiking like when I'm doing an actual Jugglebot. And it's just hassle. It's way more stuffing around. That has been a huge source of stuffing around for me with actual Jugglebot, and I wanted to just avoid it if I could. This was one of the... You may remember that a big part of what I'm wanting to do here with Butler at this stage is just to learn. I just want to try alternate ways of doing things that I have heard about as a result of doing the Jugglebot development, but haven't had a chance to do because I already made a decision that precluded me from doing that on actual Jugglebot. So now it's like starting fresh. It's like, okay, cool. What are my options here? And can I try some cool, fun, new, exciting things? One of those fun, new, exciting things is using absolute encoders everywhere. So last week I was talking about the different encoders that I was thinking about using in the different parts of this robot, where I want to have one on... Basically each motor needs its own encoder on the motor output. That's just how the motors are controlled. But then also I wanted to have encoders on the output of like every stage after the gear reduction has happened. So on this big ring here, let me change to a different view so it doesn't spin around. Whoops, wrong one. Also, by the way, there's links in the description for... Oh, actually, no, there's not. For these models. Let me share a link in the chat now if you want to check it out. I ran out of time to flesh out all my links. It's a bit of a chaos this morning. Yeah, so this stage... Hopefully that link works. I don't know if it actually will. But this stage will move up and down like this, and that's basically a gear reduction. So as this motor here can spin, I think it's around 8 or 10 to 1, so it'll spin around 8 or 10 times for each full revolution around this big ring. Of course, there is no full revolution to be had, but yeah, still the same sort of gear reduction. So I wanted to have an encoder on each of these axes, so like on each of the reductions, so that I knew exactly where the whole system is. We know exactly where the motor specifically is, and we know exactly where the entire structure is. And importantly, to be able to have zero movement on startup, all of those encoders need to be absolute encoders. And I think it's possible to get absolute encoders that work for multiple revolutions. I believe that's a thing for like a couple limited revolutions. But I'm not made of money, despite what some of my purchases may have you believe. And I already have a couple encoders that are absolute for one revolution. So all of these encoders are absolute for one revolution, which works completely fine for this encoder down here, this AS5048B. May change, more on that later. That's absolute with one revolution. So wherever this arm is, the encoder will know exactly where it is. Of course, if it loops the whole way back around, it will still say, I'm at position 0.2, like radians or degrees, whatever unit you want to use. Once it loops the whole way back around, it will think that it's in the exact same position, but of course it's one whole revolution around. But that doesn't matter for me because it can't go a full revolution around, so that's fine. Then also the encoder on the back of the motor is also accurate, is also absolute for one revolution, which is why we need both of these to know where the whole system is. Because this motor could be at a given position, and then once it rotates a full revolution around, the whole system might be here, but then the motor encoder will think that it's in the exact same position that it was before, so we need this other encoder down here to say, hey, no, hang on, we've actually entirely moved by like a unit revolution further. So we need both of these. And the reason I'm going into so much detail with this now is because using the ODrive 3.6s and this approach of having absolute encoders, if you Google anything related to this, you'll find many forums where lots of people are basically saying, I followed the instructions to the T and it's not working, why? And then it's like dozens of messages of trying to debug this and try to figure out why. And yeah, reading through this, I was a bit like, oh crap, what am I getting myself into? Like, this does not bode well. So this was one of the things I wanted to test this week. And thankfully, bit of a spoiler, it's working very nicely. It's a little bit of a interesting setup that I've got here, but I'm keen to show you. It's very cool. Just to look at comments first though, Prop Guru says, smart approach, thank you, hopefully it works. It says, for after the reduction, couldn't you use a regular potentiometer? Probably. I haven't really used potentiometers as a type of encoder before. I don't know how precise they are. I really want this to be precise as well. So I've done very rough calculations of how accurate these different axes will need to be. I don't remember for the pitch how precise it needs to be, but I know for the yaw motor it needs to be within 1 degree, which is it just like that number just popped out of like, if the ball is within what were my numbers? Where's my book? For the ball to be within 35 millimeters of the landing position with a throw that has an X, like a horizontal span of 2 meters, which is quite far. Like that is further than Ball Butler will ever need to throw to Jugglebot. Possibly to me, it'll be throwing 2 meters, but that's a pretty far throw. The yaw can be off by 1 degree. If it's off by less than 1 degree, then the ball at the end will be within 35 millimeters of its landing position. And the reason why I've chosen 35 millimeters is because that is the radius of the ball. So as long as the error is less than the radius of the ball, I figure the ball should just like roll into the hand. Or if I'm catching it, like I can easily compensate for 3 centimeters of error. So that should be fine. I believe the pitch was about the same as well, about 1 degree. So the big reason why I've chosen proper encoders on these axes here is for just making sure that that axis is precise enough. Yeah, so that we know exactly where it is when it makes it through. Yes, Alice, I'm glad you could make it. I've been meaning to reply to your message on Zulip, but I'm glad to have you back again. It's good to see familiar names, not faces, but maybe one day. Anyway, cool. Let's get into the demo. So, yes, I can't remember my numbers for these. Let's go here. All right, I've got a bit of a messy setup. Don't judge me. I've got here we go. My desk setup. There's a big ol' rat's nest of wires here. I really should have used the other microphone for this today, but hopefully this works. Yeah, did I mention as well? I love these Wago connectors. Absolutely, 100% recommend. They are fantastic. So good for doing prototyping, wiring, stuff like this. Yep. Okay, so let's look at this one first. This is the more satisfying one to see move, I think. Now, my moving for this is very limited. I haven't really been pushing it too hard. There's a lot of tuning work that I could do for these motors, but I haven't done a whole lot of Melbourne. Alice got me confused. I haven't done a whole lot of motor tuning before, but I'm getting the impression that it's very advantageous to kind of like build your system the way that you want it to be, and then tune the motor. I'm noticing this probably feels super obvious for anyone who's done this before, and I hope that it's true. If it is true, then it'll be good to get some confirmation on this. But yeah, I've noticed there have been a couple times where I've like gotten it where it seems to be good, and then I put the motor in a different context, and the tuning is just all off. So I haven't gone too crazy with the tuning on this so far because none of this setup is really exactly what it's going to be in the actual system. But yeah, so movements are limited, but they do work. And that has been on the whole time. Whoops. All right, let's go back to 7. All right, so it should start rolling up, and then wait a couple seconds, and then roll back down. How good? Very simple, obviously, not much going on, but it works. And yeah, it's very satisfying to have it move. Now, if you've watched Ayad Moose's video on these capstan actuators, you may know that these, well, and also just if you have a think about the way that the gear reduction works here, you may realize that this should have a lot of force, right? Because this is like an 8 or 10 to 1 reduction. These motors are pretty strong, so it should be quite strong. And as soon as I got this working, within about 15 minutes of me having this working, I was thinking, how strong is this? I wonder if I can stop it from moving. That was a silly thought. I should not have done that, because I kind of forgot about the fact that the main component that is transmitting... I'll run it again as well, and we can see it again in a sec. But the main component that is transmitting the movement between these two arms here is this spool here. That is, right now, that is the only component that bridges the motor side to the aluminium extrusion side. And if you want to have a guess which side I decided to hold on to try to see how strong this thing is, it was the aluminium extrusion side. Which meant that all of the hyped up for all of the crazy force that this thing can generate, all of that was passing through this little spool here, which is currently 3D printed. And perhaps unsurprisingly, it snapped. Yes, it snapped basically straight away. And as soon as it happened, I was like, oh, that was a stupid thing to do, because that was very obvious that was going to happen. But I was a bit too excited about the fact that it was working. And there's such a good handle here. This aluminium part, such a nice handle. But yeah, so this is the old spool. It broke exactly where you would think it broke, which is where the hole goes through. Yeah, so that was a little bit annoying, but there is an advantage to this, which is that I can show you the tensioning mechanism, because I have not tensioned these strings completely fully, even though it does work. I'll run this again so that so the motor will move up and down. Let's see, we'll go up. And then back down. Yeah. So actually, for reference here, I'll show you all of this as well. This is being controlled through USB. I've got a lot to talk about on the CAN bus, but we'll get there when we get there. So this is very simple. This is motor 0. This is basically, we're putting it into closed loop control, getting it to move 2 revolutions forward from wherever it starts, and then waiting a couple seconds, and then moving 2 revolutions back. Yeah, very, very straightforward. And it is over USB. And I've been playing around a lot with getting fast movements, especially out of the motor that's not rigged up to this. But yeah, I think that the USB connection is stuffing things up here. If I tell it to wait for 0.5 seconds and do 10 commands, it'll... Oh, I went to... Yeah, you'll see this in a sec. Yeah, actually, well, let's go to this now. So that's that motor. That motor spins nicely. All well and good. What about the other motor? Let's go to M1 test. So that is this guy. So this guy also spins. They both are using the AS5047P encoders, which is the one that was all of the hassle was coming up on for all of the ODrive forums that I was reading. They were not giving me too much hope, but they do work. I have not actually tried both motors going at the same time, but I can do one and then I can do the other, so I figure that they should both work. Yeah, perhaps that's a bit of an assumption, but yep. Now you may notice that there are some little indicators on here. And the reason for that is because we have a different view. We have the slow-mo view. Yes, we love slow-mo, but I'm not on here. There I am. Whoa, that's a bit of a crop, isn't it? Oh well, that's going to take too much effort to change, so you get to look at me like that. Yeah, so I have this set off so that we can see how accurately this can move around. Where should I go? Let's go over here. Yeah, so I wanted to check how precisely I can actually control these motors, because if I want to control these, as I said before, I want the yaw at least to be within 1 degree of being where it's supposed to be. How closely can I actually control these? So you may remember, I was originally planning on having the base not like that. Yes, I was originally planning on having the base like this, where it was basically... It's kind of hard to describe. It's kind of halfway between a belt drive and a capstan drive, kind of. You can go back 2 streams and see the details on this. But this was my original plan, and it was about something like 20 or 30 to 1 gear ratio on here. And I didn't really have too much of a good reason for doing this. I just kind of did it because I thought it would be cool and because it would give smoother motion, and yeah. But then I realized once I actually got these motors moving, I was like, well, hang on, they actually seem to be going pretty closely to where I'm commanding them to go. Maybe I can just put the motor directly on the axis, as some people had suggested when I originally brought this up, and kind of just be done with all of, like, that way I wouldn't even need to worry about any gear reduction stuff. I would only need one encoder because the motor would be the output. Like, it would be a lot simpler. Maybe we can do that. But the motors need to be precise enough. So let's have a look. Not that one. What do we want? 9. 9 is the wave. So I have this set up. I'll show you the code first. We are doing M1 test, so we can get rid of that. M1 test. I have already keyed in the start position, so I moved the needle until it was like exactly in line with this one, so it was like that, and then measured what its position was, and that was this number. We don't really need that comment. We are then putting it into pass-through mode, so it's nice and fast, setting some gains, which we can play around with a bit, potentially. We then step in 5-degree increments from 30 degrees down to 0 degrees, and then we go around a full revolution, and then do the same thing. And it's kind of cool. So, also, by the way, these tick marks on over here, the big ones are 5 degrees and the small ones are 1 degree. And it actually printed out kind of nicely. I'll show you, I'll make it a bit brighter so you can see it. Yeah, it actually printed fairly nicely. It was on a 0.4mm nozzle, which is currently the smallest nozzle that I have. I'm very strongly considering getting some 0.2 nozzles to do this kind of thing a bit more precisely. But it actually turned out alright. Like the fat lines, the 5-degree increments are 2 line widths thick, and the thin lines are a single line width thick. So it's not too surprising there's a bit of, I don't know, roughness on some of them, but they're pretty good. And I've measured them with the protractor as well as I could, and they seem pretty spot on. Prop Guru says, I find it's best to have an interface between motor and load to reduce lateral force on the drive shaft. Interesting. Also gives a weak link to brake in case of an expensive motor, instead of an expensive motor. Yeah, those are good points. But I think for this situation, I think that the motor just straight on the output shaft, bit of a spoiler, that's not my ultimate plan, but I do think it would work for this because there's not really any opportunity. Actually, that's not true. I was about to say there's not really any opportunity for lateral forces to come into this, but there actually are when the ball is thrown. So if this was tilted really far over, all of the momentum that this robot is giving to the ball has to come back through the base at some point. So yeah, you're right. That is definitely, I had not thought about that before, and that is worth thinking about. Yeah, I've got some more things to talk about with where I'm at right now, but that is a very good point. Okay, so let's go back to this. Let's go fast speed. I wish that I could just have like a little control station to do all of this at once. And let's run it through its thing, and I will record at the same time. We can watch it in slow-mo and see how good it is. You can see it's not quite on them. So this should be moving in 5-degree increments. It should be hitting those lines, the fat lines, bang on. And you can see it does, like here. Oh, no, missed. So it's close, but it's not quite there. And with the tuning point as well, you'll see, it's kind of annoying having the mic here and the camera over there. I'll just talk loudly. Hopefully you can hear me. Let me know if you can't hear me, and I'll do something else. We'll play back in slow motion. You can see I could definitely do some work with the tuning on this. I need to, essentially, I set the position gain to be super high because I could see, obviously, like I don't need slow motion to see that this is not lining up perfectly. And I figured that, okay, if I bump up the position gain, then maybe it will hit those target positions more precisely. So I bumped that way up, but that now has the end result of it overshoots a lot. So it's very hard to see in real time, but you'll see it very obviously in slow motion. When it does that full revolution around, it like massively overshoots. And also, yeah, for context as well, because these big ones are 5-degree increments, this whole thing, I believe, is 30 degrees. So yeah, 5, 10, 15, 20. Yeah, the whole thing is 30 degrees. Yep. The problem with recording in such fast speed is that it takes forever to find the stuff that you want. There's a lot of like nothing frames in between. Yeah, so this should work. Alright. So you can see it ticking over. It's very fast going from spot to spot. I'll go for normal speed. So yeah, this was recorded at 300 frames per second, and I believe it plays back at 24 frames per second. Yeah, even there's a bit of wobble on that. Also, that's the flickering. I don't really know what causes that. It's something to do with the camera itself and the HDMI connection. It's not in the like actual recording though. Yeah. So it's ticking over. It's getting within a degree. Like that one's like 1 degree off of where it should be. Next one, after a bit of wobble, within a degree. Yeah, let's skip ahead a bit. And then we can see the big movement as it wraps the whole way around, and it has a huge full like 30 degrees overshoot, and then lands back on. But yeah, it's not getting it's not getting straight on. I really highly suspect that this problem is because of my motor tuning. As far as I'm aware, the hardware that I have here, the ODrive and the encoders and the motors, should be more precise than this. I remember in Ayed Musa's video, I actually don't remember now that I think about it, if he like tested the output of the motor directly, but I do remember from his capstan drive, that was like super precise. However, that was after the gear reduction of the capstan, so maybe that's the reason why it was so precise. But in any event, yeah, this being reliably around a full degree off did not fill me with a lot of confidence with using this motor directly on the output for the yaw axis and for the pitch axis as well. But I'm already pretty committed to this capstan thing for the pitch anyway. But yeah, I feel very good about using these motors with a gear reduction, especially for the pitch axis. That's like a 10 or it's about 8 to 10 times gear reduction. So if this is within 1 degree, then the pitch axis will be within 0.1 of a degree, which is absolutely fine for what I need. But for the yaw axis, this does present some problems. This means I can't just go directly onto the output shaft. Stop that. Now, one other thought that I did have on this is that maybe this error was being caused by the non-linearity of the encoders throughout the whole rotation space as it moves around. And this is something that was brought up last week and it was a very valid thing to bring up, because these encoders are not perfectly linear through the whole motion. They are very slightly off. It's in the data sheet. I can't remember exactly how much it is. I believe the biggest difference is caused by temperature. Like if you move it from like negative 40 degrees up to like 120 degrees, which is like, what the heck? That's such a big range. Then the error is like a degree or something, which is quite a lot. But I thought that like maybe the encoder is slightly off axis, so possibly that is causing this problem. So I improved the way that I was mounting the encoder onto the back of the motor. I'll show you on here. I need to go back to an older version because some things have changed. I've got some cool plans, but I'm not set yet. Yeah, so this is the encoder that's reading from the back of the motor, and this is the exact same setup as what I've got on that little dial indicator test rig. So what I originally had was M2 bolts going through these holes, and these holes are 2.6 millimeters diameter. So it's possible that because there's a bit of wiggle room there, it's possible that the actual encoding part, the chip, it's possible that the chip is a little bit off axis from the magnet. So maybe that's causing a bit of nonlinearity, and maybe that's stuffing around with my readings, possibly. So I thought. So what I did is, oh my God, I changed my shortcuts recently, and I'm gonna get used to them. What I did is I drilled these holes out. I did it the old-fashioned way, drilled these holes out to be 3mm holes, and then put M3 bolts in so that they are all perfectly snug and tight, and the encoder has to be exactly where it's supposed to be. And that's what we have now. And the result hasn't changed. So before and after, exactly the same. So I suspect that this is related to cogging torque, which is basically the fact that the motor, if you've ever felt a brushless DC motor when it's off and you've tried to move it around, it really wants to sit in certain positions. Like maybe I can show you on here. That's not live. Yeah, so as I move this around, it really wants to sit in some spots more than others. And that is caused by cogging torque. So there's basically a bunch of magnets in there, and they want to stick to the coils of the stator, or yeah, the stator in this case. They want to basically stick to those, and there's certain positions where that attraction force is higher than in other places. And I suspect that this is what's causing this problem, I think. I'm not 100% sure. But I'm a practical man. I have learned that if I try to dig down to the bottom of all of my problems, then I will never get anything done. So I'm basically just taking this as a given. I'm saying, okay, with this kind of sketchy setup that I could probably improve, I'm getting this amount of control. So let's take that as the baseline and move forward with that as the assumption of how precisely I can control these motors. It's entirely likely that if I spent more time and effort trying to tune this a bit better, then I could get even better control. But if I just take this as a given, can we just work with that? Like, the easiest problem to solve is the non-problem because you just ignore that it's a problem in the first place. Procurator says, instead of reading the motors encoder on the yaw, why not rely on an encoder on the actual base? Yes, so if we have a gear reduction, so if we have something similar to what I had originally like this, there would be two. There would be an encoder on the motor itself so that we can do the motor control. And then there would also be an encoder on somewhere in the middle of the base or somewhere on the base tracking the position of the actual base in the exact same way as the pitch axis works. So that way we get exact feedback on where the base is. Alex says, I thought the ODrives did a calibration to remove that. Yes, you can do an anti-cogging calibration, which basically runs the motor through a full revolution, I think forwards and backwards, and then measures, like it has the motor on and it slowly turns it through and it measures how much attraction force there is to pull the motor out of every position that it's in. And it essentially creates a map of, okay, if I want to go to this position, the magnets are going to be try to pull me slightly out of my position, so I need to apply a bit more current to hold this position even stronger. But if I am the motor, I'm in a position where the magnets want me to be, then I can apply less current because the magnets aren't trying to pull me away. That is a thing that you can do. However, it's extremely, what's the word? Touchy. Let's say it's very unreliable, especially on the ODrive 3.6s, which are the ODrives that I'm planning on using for this. Very, very unreliable. I have never gotten it to work on any of the ODrive 3.6s, and I've tried quite a bit. Not with these motors, so maybe it's worth trying. Could be, because it doesn't take long to do. We'll see how I go. But I don't have high hopes. I don't think it will work. Yeah, even with the ODrive Pro, it is a bit tenuous. It just sometimes works and you change nothing and then run it again and it doesn't work. Even though you shouldn't need to run it multiple times, but yeah. Hello Everything says, I saw some really interesting anti-cogging techniques using the simple FSC Discord, might be useful to look at. Yeah, okay, Procurator says I can guarantee that's the issue with accuracy. Hopefully you're talking about the anti-cogging stuff. Yep. Okay, that's good that people agree. Yeah. I could do the anti-cogging calibration thing, but I suspect it's not going to work. Maybe I'll give it a go after all this suggestion. But yeah, so I am thinking, so This is a little bit kind of like using the evidence to fit my preconceived ideas. But even before doing this, I've been a little bit dishonest about the order of these things. Even before doing this, I realized that this setup is kind of not ideal. I don't really like having this motor above the plate here. It just kind of gets in the way of having all this stuff. Like ideally, this stuff would be more in the middle of the ring. Just from like a kinematics point of view, and also a wiring point of view, I've been thinking a lot about how to get the wires around the different places here. It's going to be a lot simpler if the pitch axis and everything on top of that is as close to the center of this ring as possible. And that's going to be very hard to do with the motor where it is. Now, I spent quite a bit of time trying to think about a way to do basically this, or something like a capstan drive where the two axes are perpendicular to each other. So this motor would be up on, like if I draw it on here. My thinking is that if the motor was here with its like axis pointing out here, then we could if there was some way to like run the string up and around there and then down around the other side, that would be pretty cool. And that would solve a lot of these space problems by just having the motor be a bit more tucked away. But I couldn't figure out a good way to do that. And I figured it was a bit of a waste of time spending too much time on that. So now I actually haven't CAD'd this because I've been a bit busy with other things, but now I am planning on, actually I might have, I think I CAD'd a little bit of it, the general idea. Yes, so I'm now thinking of putting your motor below the ring up the top, and that allows, you can see how nice this looks with everything centered. I believe this ring is actually also a little bit smaller. But then having this offset a little bit, because that will mean that the middle itself is open for cables and other stuff to run through. And then using a belt drive, because I've been pretty keen to do a belt drive. I've never made anything that's belt actuated before that's actually worked. This would be like the most simple belt actuation you could possibly have, where it's basically the largest pulley that I have, which is 60 teeth, paired up with the smallest belt pulley that I have, which is 18 teeth. It would basically just be that. Direct motor on the small one, the main ring attached to the big one, and just a single belt loop between them. That will be my first experience with belt drives, and hopefully I don't fuck it up. I give myself pretty good odds of getting this to work. Yeah, so that's my plan right now, is to have a 3-to-1 reduction. And that means that this 1 degree of error that we're seeing is not really an issue, because if we third that, then it's fine. Alice says, I would have thought the PID loop would correct for it slowly anyway. Yeah, you would think so, but the anti-cogging is, well, the cogging torque is pretty strong. And also, actually, something that's very worth keeping in mind here is that I'm only running this off of 12 volts. And I will talk about why more a bit later. Prop Guru says, move your hash marks closer or further from the needle and you'll see a difference in accuracy, or remove delay between movements that incorporate changes in direction. Move your hash marks closer or further. Why would that make a difference? Closer or further from the needle and you'll see a difference in accuracy. Because they're all like 1 degree apart anyway. The distance from the axis. Part of the reason why I put these so far away is just so that I could actually physically print them. Because if they're too close, then they get too small and they just can't print. But they're still a degree in angle apart. And remove delay between movements and incorporate changes in direction. Yeah, how many wire connections will you need between arm and base? I'll answer the wire one in just a sec. But on the delays that you just mentioned, something that I think you can actually see on this, let's run this again. I won't record it in slow-mo, but we can watch it. So all of these pauses should be 0.8 seconds. All of them, every single pause should be the same amount of time. But you can see that it's not. Like that pause then was quite a while. It always kind of goes like tick, tick, pause, tick, tick, pause, tick, tick, pause. And I have no idea why. Like my code doesn't do anything about that. Like my code is always just like do one thing, set the position, wait for a bit. Set the position, wait for a bit. It's always the exact same. And the sleep time in this case, whoops, is 0.8 seconds. So it shouldn't be kind of breaking up like that. But what I've been attributing this to is the USB connection. And this actually segues on very nicely. I'll get back to your wire connections question in a bit, Prop Guru. Remind me if I don't, because I do want to talk about that. But this is too nice of a segue to miss to the CAN bus. So I was getting all these problems with the USB, and I'm like, oh, this is just a mess. I'm not going to use USB later anyway, so let's just try the CAN bus. Let's see if that works. And you may remember that I have quite a history with setting up CAN buses, and it was not a very good history, I don't think. It was filled with troubles. However, now that I actually kind of understand what I'm doing, it was just so straightforward to set this up. With one big asterisk, which is that I am pretty sure when I was using the ODrive 3.6s last time, I'm fairly sure right at the end of when I was using them, I think I might have cooked the CAN transceivers on every single one of them. And I'm really racking my brain to try to figure out what exactly I did. I remember I mentioned it in a video or a stream at some point, but I don't remember when. I don't remember what the event was that made me. All that I remember is that I have a very strong idea that these CAN transceivers are broken, but I don't remember why I think that. And that checks out with my testing so far. So let me show you my setup. We want 5. Nope. I don't know what that number is, but all right. So my setup here, this is where the rat's nest comes into full glory. We've got a lot of things going on here. So over here, I've got a Teensy, and that is what I'm planning on using for the brain of this unit. So this Teensy will, let me show you my preliminary wiring diagram. And hopefully things will make some sense. Okay, yeah, this should explain some things. All right, so we have the Teensy over here. Let's go. Oh, we already are. CAN 1 is a CAN bus that is coming from Jugglebot computer. So that will carry with it the signals from Jugglebot, and that will be commanding Butler when to throw and where to throw to. Very, very minimal communication, hopefully, from between these two systems. It shouldn't need to be much more than throw to here at this time. Should be about all it is. Also, on that line, in that bundle of cables, there'll be 4 cables: CAN high, CAN low, 12 volts, and ground. And those 2 will just be there because that's what the ODrive Pros use, and so they've already got that wired up. I just need to run an extra length of wire up to Butler, and then we'll get 12 volts. And that's why I'm planning on running all of this off of 12 volts, because I've already got that. And I believe the current should be fine. My power supply that is supplying this 12 volts is either 3 or 5 amps, which should be plenty. It's not really powering anything else right now, I don't think. It's only ever powering the ODrive Pros of Jugglebot when Jugglebot's not actually on. Once the main power to Jugglebot goes on, then those get powered from the main power supply. So pretty much all of these 3 to 5 amps, I can't remember which it is, all of that should be going to Butler for it to use. And that should be heaps for what it needs to do. I mean, this isn't going to be rocketing around or anything, so it should be able to just take it easy. I will have to have some kind of power, like a, what are they called? Like a buck converter or something like that to get 5 volts down to power the Teensy, but that shouldn't be too tricky. I've already done that on Jugglebot. The Teensy will then also be connected to CAN 2. So I'm going to have a second CAN network that will communicate. That would be like a Butler specific CAN network. And the reason why I'm separating these two is because there's already a lot of traffic on Jugglebot's CAN bus, and I don't want to have to risk. I don't want to risk having messages that basically get sent to the wrong address. There's a lot of because there's already so many messages on Jugglebot's CAN bus. And I will be introducing the ODrive 3.6, probably more on that later. I'm worried that the firmware on the ODrive 3.6 will have some collisions, essentially, with the ODrive Pro stuff, and I figure it's just easier if I keep them separate. I just want to separate these concerns. It does mean that the Teensy will need 2 CAN transceivers, but it has 2, I believe. I think it actually might have more. It has three CAN transceivers, or CAN interfaces. So that should be fine. Yes, so the plan is to have this TNC controlling everything the ball butler does. So it will be sending out the commands for where the yaw motor needs to go to, where the pitch motor needs to go to. It'll be getting the feedback from those motors and then making sure that everything's all hunky-dory. And yeah, so I figured, okay, given that the USB connection is kind of stuffing up, let's try running the CAN bus through the TNC. So that's why I have the TNC there. And I'll go back to this wiring diagram soon. Let's make this a bit bigger for me and go back to here. Prop Guru says that and some bounce. Definitely a cogging issue. Also, like you said, yeah, USB communication. USB is crap. If you're doing anything with any of this stuff and you're using USB and you're having problems, definitely try a different type of communication. USB is so bad. Not good. But yeah, we've got TNC over here. All of these green and yellow twisted cables are the CAN cables. So we've got one that is going to, you can see there's a little board in here underneath the XT60 connector. I don't want to move things around if I'm not looking at it closely. But yeah, you can see there's a little board over there that is connected with the micro. Let me get my pointer. I shouldn't do that with a metal one. I need a plastic pointer. I'll use the handle. There we go. So this guy is another CAN transceiver that is being sent to this computer. Haha, it did work. Nice. And this is my CAN logger. So so this is basically monitoring the CAN bus and looking for messages. Right now you can see that nothing's going on because nothing's going on. But it should be. But more on that later. I've got a lot of things this week. Lots of stuff going on. Also on that CAN bus is the ODrive 3.6. This guy tucked in here. That is also connected. Yes, just wanted to double check. So, and that is actually on. So right now, that ODrive 3.6 should be spitting out messages. But as we just saw in our viewer, there's no messages there. Well, there are, but they're old ones. Let's clear them. There's no messages there. Nothing's being sent over the bus. So what gives? Is the bus working? I don't know. Let's find out. I have the TNC set up right now to spit out. It's trying to read it's basically asking the ODrive 3.6, hey, what is your encoder position and maybe voltage or something like that. I basically just got it to ask for like 2 types of message, even though these messages should be being printed out by the ODrive 3.6 anyway. It should just be spitting these out as part of its like heartbeat messages, which I have checked. They are on and they should be publishing. But yeah, so the TNC is basically publishing some messages. So let's turn it on and see what happens. All right, TNC's on and it's publishing its messages. And we can see that they're coming through. There's 2 messages at cycle time of 10 milliseconds per, 10 milliseconds. I can't remember if this is 10 milliseconds between the messages or if it's the hertz. So it's either 100 hertz or 10 hertz, but whatever it is, it's whatever I've set it to be on the TNC, I can't remember. But they are publishing and they're coming through. But the ODrive messages aren't. So the CAN bus itself is definitely working. Huzzah! I can set up a CAN bus correctly. This is nice to know. Honestly, it actually is the... yeah. Given this, getting to this point took me like at least 6 weeks previously, and this was like 2 hours yesterday. Oh, so good. I'm actually learning something. But the ODrive isn't working. So I figured at this point I could just like vaguely remember that I had this problem earlier with the CAN buses on the ODrives. I'm like, I kind of thinking that maybe it's still fine, maybe it's not. But I went through and started some debugging. And let's have a look. I can show you my debugging. Nebby says, definitely 100 hertz with how fast the count is rising. That's a very good point. Yes, yes. So it's 10 milliseconds per, like in between each message. So here you can see my oscilloscope, and this should be live. Let's try. Let's probe something. I don't know. What should we probe? Actually, yeah. Let's. Yeah. All right. I'll turn. So I've just turned the ODrive off. So now we're only looking at the messages coming over from the teensy. And I actually do have some questions about this, and I'm not too sure what's going on with some things, but I do think I've gotten to the bottom of the main problem. So with my setup here, it'd be good if I could show you the camera as well. How might this work? If you're seeing this, could I put the oscilloscope down the bottom? That works. Hopefully that's visible. Yeah. All right, cool, nice. Yeah, so I'll probe one of the CAN lines, doesn't really matter which one, and you can see what it's supposed to look like, or what I think it's supposed to look like. So this is on CAN low. This is CAN low for, like, on the transceiver board that's going to the logger computer. And I need to roll up my sleeves. Actually, one other thing that you may notice here, I'll just quickly zoom out. I have a nice new blue mat here. This is so that I don't zap things, and I've got a wrist strap, so that if I connect this up, I can put my wrist strap on, and I will now no longer zap things, which is very comforting to know, because I believe I have zapped things in the past without realizing it, but now I am ESD proof, which is very nice. It's good to know that I'm not going to break things. Yeah, that was a bit of a thing, but it doesn't really matter for now. It's all set up, and I won't damage my desk surface as well, which is kind of cool. So I'll just leave this on, because why not? But yeah, so on CAN low, this is our signal. So we can see here, I believe this is like the two frames. So like the first frame is all of like this stuff, and the second frame, the second message is the stuff afterwards. I don't know why it goes up above, like there's like the main line that it's on, and then it goes low, and then it goes up above that line. I don't really know exactly why, especially because when I turn the ODrive on, that flattens out. So now the ODrive is on, and the only difference that we see is that that line rises up. Not 100% sure what's going on there, but it does. But anyway, this is what the CAN message is kind of supposed to look like. Like there's a bit of up and down, a bit of spacing between them. You know, like there's data there essentially. Now, when the ODrive is not publishing, then we don't see these signals. And now when the teensy is not publishing, we don't see these signals. But we should be seeing the ODrive signals from here, because the ODrive is currently plugged in and on and connected to the CAN bus. Its signals should be coming out. But if we zoom out, we don't see any. We just see the teensy's message at whatever the rate is, 100 Hertz for each of them. So there's a lot of space there for the ODrive messages, but there's just nothing there. So I got to, I don't know, having a look around, and then I realized that I was looking at the ODrive board itself, and I was having a look around, and then I saw on the back, this is not the same one as the one that's hooked up over there, obviously, but it's the same idea. This chip here is the CAN transceiver chip. And you can see that I have fucked around with that. I have done some hand soldering on that boy, and that's the case for all of them. So I actually think I might have broken the CAN transceivers multiple times on these ODrives, and replaced them at some point, which I vaguely remember, but not too specifically. And because I wanted to get a bit of a better idea of what was going on here, I pulled up, let's go to here. I had a look at the data sheet for this chip, and we can see that this is where all of the pins are oriented. And so I figured, okay, maybe, is the chip even getting power in the first place? Let's have a look. Let's probe that. How do we go back to... Yeah, so let's probe the power. So the power is the third down. You gotta make sure you get the right one. So it should be... that guy. And no. Oh, it's off. Okay, we weren't getting power then, but that's probably because it was off. So let's try turning back on, and also I'll give you the oscilloscope view so you can actually see what I'm seeing. And let's make it a bit bigger. Yeah. Yeah. Cool. So that was sitting up at 3.4 volts. Cool. So we're definitely getting power to the CAN chip. Is it sending out its messages? Well, it should be sending out over CAN high and CAN low. So let's check those out. Let's start off with CAN high, so pin 7. That looks pretty good. Let's zoom in a bit. I'm going to zoom in this way. Yeah, that looks good. Let's zoom in a bit more so we can actually see the messages. Yeah, nice. A little bit rough, but at least it's getting something. And again, those look like the same messages that the Teensy is sending. So it's not actually sending its own messages, but it's at least receiving, like it's present on the bus for those messages. But if you have a look at CAN low, it's not quite as nice. And that is, let me just double check, the next one down. What is that? That is garbage. Garbage data. Whoops. Nothing. Let me just double check. Sorry, that was actually CAN high. CAN low was the one from before. So CAN high is just nothing. But alright, this is actually CAN high from the transceiver board. I'm just realizing that I should have checked both. Yeah, something weird is going on. Sorry, so this is my CAN high signal. This is testing on the transceiver board. You can see where my hand is. On the transceiver board that's going to the logger. So by the way, all of these messages are still coming through, but my CAN high signal just looks cooked. And again, so this is power off. ODrive is off, but the Teensy is on. ODrive is on, and the Teensy is also on and publishing. So there's something weird going on, and I think it's related to the ODrive. So let's try removing the ODrive from the system and see if the CAN high signal is clean for the Teensy's output. Thanks to these Wago connectors, this is very quick and easy to do. Alright, so now the ODrive is disconnected from the CAN bus. Let's need to make sure that the grounds, I think the grounds are fine. Yeah, let's try it. Yeah, alright, interesting. Okay, so CAN low, again, is fine. CAN high looks a bit weird. Looks very weird. And I'm not entirely sure why. So I've obviously got a little bit of figuring out to do here. However, I'm 90% sure that the problem is related to the ODrive 3.6 because I have put the ODrive Pro in. You'll notice I've got an ODrive Pro sitting on the corner of the desk over there. That, once I connected it in, I could see its messages coming across perfectly fine, and I could send messages to it from the Teensy, and I could receive messages from it to the Teensy. All of that communication was working perfectly fine. So I'm fairly sure that the problem is related to the ODrive 3.6. And I'm thinking that I am just going to try to replace the CAN transceiver board with one of the ones that I have lying around. I got a strip of them last time that this happened and seemed to be able to replace them perfectly fine with my soldering iron, which I'm not too keen on because it's a pretty tight little area in there, but we'll see how we go. I obviously managed to do it before. So I'm hopeful that once I swap out that transceiver chip, hopefully the 3.6 should be able to communicate over CAN and everything will be fine. We'll see. If that doesn't work, then I might have to use ODrive Pros for all 3 axes here. And then, I don't know, I guess just save the ODrive 3.6s for something that doesn't need CAN, I guess. Which is a bit of a bummer. But hopefully swapping those chips out will fix this. Yeah, strange problems. As always, with CAN. Yep. Yeah. Okay. So, John says, CAN is differential. The signal is CAN high minus CAN low, which is why the high and low look a little weird when referenced to your ground. Yes. Yeah. Yeah. So, yeah, what John was just saying is that this message, if you're not familiar with CAN, the reason why it's so robust and the reason why so many, like, it's used in noisy environments, like automotive environments, and the reason why, like, those cables, you could see the orange and, sorry, not the orange, the green and yellow cables in here, I've twisted them all up. The reason why is because it's a differential signal, and one line will go up when the other one goes down. So if we see, oh, yeah, you can look into it basically. One goes up when the other one goes down, and so you're actually, like, the actual signal itself is the subtraction of one from the other, rather than just one or the other, which is what I've been looking at. But it's, I wouldn't have thought that just connecting the ODrive would, or sorry, I wouldn't have thought that powering on the ODrive would, like, raise that level up. And I noticed similarly when I had the ODrive Pro going on there, the CAN bus shot up by quite a lot. I think my grounding may have not been perfect with having everything grounded exactly the right way it's supposed to be. But thankfully, these CAN transceiver boards, I believe they have a common mode voltage. They allow up to like 27 volts or something of common mode differential, which means that, like, the pair of them, the signal itself is in the difference between the signals, but, like, the two of them can together waver quite a lot. And I believe for these transceiver chips that I'm using, and the ones that are probably broken on the ODrive 3.6s, from memory, it allows for a bit over 20 volts of that kind of wavering for the signal to still be detected perfectly fine. Yeah. But yeah, you're right. That's probably why the line is kind of going, why the line looks weird on the two individually. From memory, you cooked at least some of the CAN transceivers by disconnecting the negative power. That was it. Yes, one of the power rails came, like, yeah. The ground came out on one of the ODrives. Yeah. And yeah, then power could go through the CAN transceivers instead of where it's supposed to go, is like through the power network. Yeah, you're definitely right. He said, and John says, there's something going on with the CAN ground. Yeah, I need to, because I've been, like, connecting and disconnecting things so much in this setup, I think the grounds have gotten a bit messy. Yeah, that could definitely be improved. But in any event, I'm like 95% sure that the CAN bus is working and it's fine, but the ODrive 3.6 is the issue. I'm fairly sure. Now, I'm very, very much in two minds about this. This is a very frustrating position to be in, because my life would be a lot easier if I did use the ODrive Pros, exclusively ODrive Pros. It would mean that there's only one like database for messages. So to give you a bit of an idea of how I'm planning on setting this up, if I show you this one, this is my teensy code right now. The way that I'm planning on this working is I basically have a Butler main script here that will, how do I get rid of this? I'll have a Butler main script that will do the actual, like, the big computation stuff. And then I'll have these little modules or libraries that will contain all of the commands to interface with the ODrive 3.6, and then also for the ODrive Pro, if I do have both types. And this just contains all of the available commands that I could possibly send to this type of ODrive, and then it structures the messages properly to send those correctly. So then in my main script, I can basically just call set input pos, and then give the input pos, and it will just do it, rather than having to replicate this. But because the two ODrives have different firmware, this code would need to be different for the ODrive Pro and the ODrive 3.6. So I would need to have two of these, one for the 3.6, one for the Pro. That should be fine, But it would be a lot simpler if I didn't have to have two, if I just had to have one, and it's less stuff to maintain, less chance of little errors getting through, all that sort of stuff. So it would definitely be simpler with ODrive Pros. Also for physical reasons. So if we look at the CAD, someone, I think Prop Guru noted this before, that I have, just to kind of see how it feels, I have mounted the ODrive Pro onto the back of this motor here. So this would mean that we're using the onboard encoder from the ODrive Pro to control this motor in exactly the same way that we're doing for the hand motor over here. And then that it's possible that the ODrive Pro is a lot better with having two encoders. So you can actually give it the commutation encoder, which would be the one on the motor, and then also the load encoder, or the one that's actually like after the gear reduction. You can give it both of those encoders, and as far as I can tell, it should like prioritize the end result position, like the after the gear reduction position. But I don't know if I feel too comfortable doing that. But this would definitely simplify some of the wiring. Like I wouldn't need a second encoder here. Like that encoder just goes away. I just put the ODrive there. The wiring becomes a little bit simpler. There's a little bit less going on there. Yeah, I'm very torn about it. And it would basically be the same thing over here. So we'd have the ODrive probably sitting directly underneath this motor, because why not? And then a separate encoder on the output. Yeah. But I really don't want to use all three of my ODrive Pros because I want to be able to save them for other things. And one big thing that's on my mind is that I have two ODrive Pros sitting around, not doing anything at all, but one of them, the third one, is in this old prototype, and I can't bring myself to take it apart. It is like buried in there. You may remember this from quite a while ago. This was the plan for the hand of Jugglebot, and we had this really neat, this was like the start of the capstan drive exploration. We had this capstan down here, so as this motor spins, it brings the hand up and down. This obviously had problems, and we didn't end up going with it, but you can see the ODrive, he's buried in there, he's deep, and I don't really want to take this apart and get him out. So I'd prefer to not use the three ODrive Pros if I can, even though it would be simpler in many regards, which is a very tough decision to be in. I wish that these things were just like free or very cheap. Yeah, that would be great if I could just have a whole bunch of motor drivers and then not have to worry about scavenging bits. Because honestly, I think if I didn't, the main motivation for me to use the old ODrive 3.6s is just because it's more like financially sensible, I think, which I think is a bit of a shit reason to do stuff like this, but it is what it is. All right, cool. So yeah, CAN works. I'm pretty sure ODrive 3.6 is cooked, but I should be able to just change that chip out. I'll try to do that later today. I will try the anti-cocking thing that Alice and Prop Guru were suggesting. I think it's a very good idea. But let's go back to let's look at the CAD now. So I've been hard at work on the CAD, and I've got a couple different things to show with this in different versions. The main one thing to show while we're here is, of course, as I mentioned before, I'm wanting to have the yaw motor underneath the plate. So it'll be hidden under, there'd be like a box kind of thing covering all of this up. This guy here is a big heavy duty aluminium alloy rotating bearing plate, which they seem pretty good. I was trying to find like really big, what are they called? Angular contact bearings, like super big ones, but they are extremely expensive and like really large in like the other dimensions. But this looks pretty good. I think these are supposed to be for like lazy Susans and that sort of thing, but they seem like they should work like completely fine. And because I don't know exactly what size I need, I just bought one of each of these. So I've got a 4-inch, 6-inch, 8-inch, and 10-inch. And the 10-inch is actually perfect to sit underneath the ring like this. So the two diameters will be identical. So this would allow for this guy to spin like this. The mating here is a bit weird, so things aren't moving quite the way they should. Yeah, so I think that will probably be how the base is actuated, how the yaw is actuated, I think that this will work quite nicely. I need to flesh out the mounting of the belt drive stuff in here, but I think that that shouldn't be too hard, I think. More importantly, I have also, so this is how things, okay, this is another thing I wanted to mention. I asked a couple weeks ago if anyone knew of any way to have a shortcut for changing the views here. You can go shaded with edges, and you can just see above my camera here, just behind the camera, there's a translucent option. And if you click translucent, then you get this. And it's like, this is very handy. This is obviously not very handy for a lot of cases, but this is super handy for some cases if you want to see particular things. Turns out there actually is a shortcut for it. But to get to those shortcuts, so just very quick interlude, you have to go into your account, and then in your preferences, down here is where all of the shortcuts are. So this includes every single shortcut that is possibly available to you, including the ones that are unassigned. But if you just go into here, and then there's some thing for keyboard shortcuts, I don't know what it is. There's some way to bring up keyboard shortcuts. Here it is. Over here. But this only shows the assigned ones, which is so strange, in my opinion. So if you don't see a shortcut, if you don't see something in here that you want to make a shortcut, then check in your preferences and it might actually be there. So I have now put shaded with edges as Shift 8, translucent as Shift 9, which means I can very quickly on my space mouse, I've got those keyed up, so I can change between these really easily, which I'm a big fan of. But it means that my section view button is a different spot now. But yeah, so this is how things were before, where I had, oh, actually no, it's not. Where is that one? So up until now, I have had, I'll show you, fairly sure this one is. Previously, when I was mounting the pitch arms, those axes, I was using 2 shoulder bolts, and that's what's currently set up on the pitch axis right now. Come on. And that looked like, see, I've got to get used to my buttons. That looks like this. So we had one shoulder bolt on this side, there's another bearing in here, one shoulder bolt on the other side, and our magnet for the absolute encoder sat on the outside as it needs to. It has to be on the end of the axis. And this was kind of good, but I mean, you can probably see in this camera view that I can wobble that. I don't know if that's really coming up super well, but actually I want to show you other stuff on this. So I'm actually going to unplug this and I'll show you on the other camera. Yep. Let me just very quickly, I've got those connected up with the DuPont connectors, and I just want to quickly take a photo of them so that I can put them back more easily later. Definitely recommend taking lots of photos of things when you're taking them apart. Alright, so here we go. This is cool, like it's good, but it's not super solid. Like I mean, you can hear it at least. It's kind of hard to see. But I can wobble this back and forth very easily, and it's not very solid at all. I suspect part of that problem is because these parts, like all of these parts that are printed, were not printed with strength in mind. I just wanted to get them done so that I could make the prototype. So they're not super strong, but I suspect part of the problem is also how I've done this connection in here. Having these 2 shoulder bolts means that they can twist independently of each other, and yeah, they're only into the printed parts by like less than 20 millimeters, so there's a lot of yeah, the printed parts are obviously not 100% stiff, so even if they flex just a little bit, that's going to mean that the whole thing can move quite a bit. And there were some very good suggestions from people to change this to a single straight rod, which I think is absolutely the way to go. This means that for either of these 2 arms to flex, that rod would need to bend, which if it's a steel rod, that's not going to happen. So I have bought from AliExpress some, they haven't arrived yet, but some M8 smooth rods with tapped ends, which is kind of cool. And I'm very strongly considering swapping over to this. So we've completely flipped things around. So before, the shoulder bolts did not spin. They were fixed to the main ring and the arms spun on those shoulder bolts. But now it's, well, in this version, it's the same thing. So the two arms spin on the bearings, but I'm actually very strongly leaning towards doing it a different way, where the two arms are fixed onto the shaft and the shaft rotates with those arms. So now we have some bearings in the main ring, which is supporting the shaft, as well as this bearing here would be supported by something on the base, and these two bearings on the end would also be supported by the base. Yeah, this means, yeah, so the shaft will be rotating as well. This does mean that I need to change the way that the encoder works. So this will be using this through axis encoder, which is another absolute encoder. I don't already have one of these, so I haven't, and I haven't bought it yet because I'm not fully sold on this idea yet, and those encoders are kind of expensive. But I'm very strongly leaning towards this. I think this will be a bit easier to assemble, and it should be rock solid. Like this should be completely bomber. The way that this would be held in place, so like, the way this will be held in place is that you can see the two arms have slots on them, and there would be bolts that come through here. Ideally, these would be square nuts, but I don't have any square nuts that are M4, so I'm using T-nuts instead. I feel like they should work. I think they should actually work better than square nuts, but I've never, I don't know. The T-nut should just slot in there, and then it shouldn't be able to spin is essentially the main thing. So these will be clamped onto the shaft, and then to hold the shaft in position sideways, because as it is right now, it should just, the whole thing will be able to just move side to side. To constrain that movement, I'm planning on using these bearings in the end. And these will just be normal radial bearings, which is probably not the best application. Like these should ideally be angular contact bearings or even thrust bearings, because the plan will be to use these screws, these bolts in the end here. Let me actually do it like this. Let's get the shaft as well. The plan will be to use these bolts in the end to essentially clamp the shaft into place, so that the shaft will be pressed into the inner race of this bearing, and the outer race will be held by something on the base, and this will just be fully constrained. It won't be able to move anywhere. And I really like this. So these cables should just be able to very easily run straight down to the controllers down in the bottom of the base. I mean, we can see once we put this in the base, like that's right there. It's peeping out. It's ready to go. And this is another reason, this is a big reason why I wanted to have all these cables in the middle. Oh, sorry, all of this top stuff, I want this to be in the middle of the base, so that when I run these cables through, they don't twist around and kind of run amok. If they are in the center, then they're going to be traveling less. They're just going to be twisting instead of moving. So I think that that should be a lot more safe. Yeah. Yeah. So you can see as well that I have hollowed out the main ring. I don't know why I didn't do this before. I knew before that I needed a gap, and you can see that I've like in the old prototype, I've like thinned out this area in here, because once it's all put together, there's going to be stuff in here that's going to collide with that wall if it's not indented just a little bit. But I don't know why I didn't just like commit and fully hollow that out. I think it looks way cooler fully hollowed out like this. And this means that I should be able to run the cables from, my plan is to have all of the cables from the motor and the encoder. If I'm not using the ODrive Pro, then all of those cables will run through here. There's a nice little cavity in here, and I want to talk about this in a sec as well. Those cables will run through this cavity down. I currently have this side open, but I suspect it will probably actually be this side that will be fully open. Those cables will run through there, through that little opening, and then down through a hole in the middle here somewhere. And hopefully that will keep them from getting tangled up and everything. Hopefully. Yeah. Yeah, so the main mechanical changes have been the positioning of your motor to be under here, and then changing over to having the shaft, having the shaft embedded the rings, in the arms, I think should work. Now, all right. One thing I want to talk about is that if I do use the ODrive 3.6 and have this set up as it is, so there's no ODrive Pro on the end here, if I do use that ODrive 3.6 and I'm still using the same encoders that I'm using now, which I see no reason why I wouldn't, then we have a slight problem, which I think is actually a blessing in disguise. It's an opportunity for learning in disguise, but in other words, in different phrasing, it could be a problem, which is that if we use the encoder, the exact encoder that I have now, like the evaluation board of the encoder, then that looks like this. That's this rectangular board. It's got the chip on it. It's got all the header pins and everything. It's in there, but you'll see that there is nowhere that I can put this where it doesn't conflict with either the mounting rings for the motor, which is a problem because I need to be able to attach the motor, or the cables of the motor. I could have the encoder pointing like up, like out this way, but then that's going to mean that the cables have to like go up and around, which is going to be kind of janky. It's not ideal, basically, with the board being shaped the way that it is. So I'm very strongly considering making my own board, because this is something I've wanted to get a little bit more practice in. And I've made this like little prototype of the outline of what the board could look like. So if I make the board like this with the, it'll be a very, very, very simple board. I mean, you can see these evaluation boards. It's just like basically the chip and like 2 resistors, and that's it. Very, very simple. So hopefully I wouldn't muck that up. That will then sit perfectly into this arm that I've made in here. So that sits nicely in there, and then I can run the cables out through that little channel that you saw in the section before, through here. These cables will run through here, and then come down, and then out, and go down to the controllers, is the plan. That does require a custom board that I'll have to make myself, but to be honest, I'm kind of keen for it. I want to get some practice with this, and I should be able to get them for free as well from JLC 3DP, or whatever it is, JLC PCB. So yeah, very strongly leaning towards that. But again, if we use the ODrive Pro, I won't need to do that. It'll get rid of the custom board because I'll just use the ODrive directly on there. So I've got a lot of thoughts and a lot of considerations to make. But they're all kind of good options. So I think it's a good position to be in. Now, before I forget, I do want to show you the tensioning mechanism here and how satisfying it is to get it to have it work. So you hopefully remember that the string that runs over the main ring on this surface here comes down and goes through, and then wraps around like this hole. This is where the translucent view helps. Aha. This hole comes down through and it opens up in here, and then it wraps around this drum. Like there's the inside section of that drum. Let me do this. Yep. So it wraps around in here. But then to actually tension it is where these ratchet arms come in. So all I need to do, if this string is a bit loose, which it actually kind of is right now, like there's a little bit of backlash in this as it is right now, because I wanted to show you how cool this is to tension. And I made this little tensioner tool, and all I need to do, there's 3 screws sticking out the end of here. Those 3 screws made up with the 3 holes in the ratchet, and you just put them in, spin it a couple times, and then it's tight. Like that is tight now. And that's it. I just bring in my tool, do like 2 or 3 clicks, and then the string's tight again. So whenever there's any like slack that's built up, which usually shouldn't happen, but I did have a case before where I accidentally overran the motor right to the very end, and it was trying to like push past the end limit. So then it was like really stretching out the length of string that it was tensioning against. So that made the string stretch, and I was like, oh no, that's annoying, the string is stretched. All I need to do is grab my little tensioner, 2 or 3 clicks, and then it's tight again. So yeah, works extremely well. I have 0 complaints whatsoever. If you ever want to tension a string, I strongly, strongly recommend using something like this. It is so easy to interact with, and like clean as well. When it's done, you just put the tool in, done. Take it out, clean. I really like this design. Yep. Okay, so that's most of what I wanted to talk about. There are two other things. Actually, one, to get to a question that Prop Guru asked earlier about how many cables there are running from the section up here down to the base. That is a very good question, and I do have some things to talk about that. There will be a couple cables, definitely. So at a minimum, we're going to have 3 cables for the motor, the 3-phase cables. I'm planning, there should be enough space in this cavity in here to fit a ferrite ring. So I should be able to put those 3-phase cables through the ferrite ring in this little cavity in here, which will be nice. So there'll be the 3 motor cables. The cables, let's get rid of the ODrive Pro because hopefully we won't be using that. There'll be the cables from the encoder, which this is SPI, and I have heard a lot of things about SPI being a bit susceptible to noise, and especially in this situation, the encoder cables are going to be running right parallel next to the motor cables for quite a long stretch of their length. And that's really not a good idea. If you're having your clean encoder signal lines going parallel to your noisy motor lines, that's a recipe for noise problems. So I have bought some, it's actually arrived quite quickly. I bought some lap cable, and you can see the code for it here. It is 4 by 2 by 0.25 plus 2 by 0.5, which is a very confusing cable, which is very confusing like code for it. But essentially this means that there are 4 pairs of wires in here that are twisted. Each pair is twisted around each other, as well as 2 other cables that are thicker that are also twisted. So I'm thinking here I can use the 2 thicker cables for power, so like it would be 3.3 volts and ground for the encoder, and then the other lines I can use for the 4 SPI lines. So we'll have like the chip select, MISO, MOSI, and the clock one. And this should be like the most noise-proof system I could possibly have, or the most noise-proof cable that I can possibly have. And from what I can tell, the best way to do this is to have each of those 4 lines with each respective twisted pair, they will be twisted with ground. So it'll be like MISO and ground twisted up, MOSI and ground twisted up, clock and ground twisted up, and the chip select and ground twisted up, as well as power and ground twisted up. Now I will need to be a little bit careful with how I connect these grounds together, because now we're going to have like 5 ground cables coming through here. And I believe the best way to do that is to have them all meet at like the encoder end. All of the grounds will meet. There'll be one little offshoot from that will go to the encoder itself. And then on the other end, on the controller end, all of those grounds will meet and go to like the system ground on that end. I think that should be fine. But yeah, I think that I will have no noise problems with this. And this cable should fit in the cutout that I've made in the model, which will be nice. Yes, so there'll be one of those coming through. That will come through here along with the motor cables. There will also be, because we'll be using this encoder, these cables, I don't know if that really counts as going from above to below, but they'll be sticking out and going into the base down here. And then we will also have cables from this motor over here. So this will need the CAN cable, which is basically the same as that green one that I was just showing, except it's purple. CAN cable, and then the 2 ODrive power cables. So we'll have power and ground coming out up here, CAN cable coming out down here, and both of those will need to come down and through. So we'll have a total of, 4 groups of cables coming through. So power, CAN, motor power, and encoder. So there will be a bit going through, but hopefully it shouldn't be too hard to kind of tuck them in so they don't get tangled up. Yep, we'll see how we go with that. Now, the second last thing that I want to mention is following on from last week, where, let me actually turn this light off, where we were talking a lot about the possibility of using a bumper to stop the progress of the hand. And what this would look like is up for discussion, but the general idea is that Rather than my initial plan was to have the hand just be sliding freely along this linear rail, and then you can like after it's done throwing, the motor will just slow the hand down, and then it will come to the stop, come to a nice clean stop just before it hits the bumper in the end. Nice and perfect is the plan. But some people had a good suggestion, which is that because this system is only ever throwing the ball, it's never catching, we don't really need to actually slow the hand down with the motor. Instead, we could potentially have a mechanical stop. So the hand basically just slams into the end and is all of that energy is mechanically removed from the system rather than using the motor to try to brake. And that has the advantage of potentially massively reducing the length, maybe not massively, but potentially reducing like half of the length of this slider here, because we no longer need to slow the motor down. We don't need as much space to slow the motor down in, because we can just brake it mechanically. And there have been a lot of very cool options here. I have been meaning to, and I haven't gotten around to it, to calculate the amount of energy that the hand will have the amount of energy that the moving part here will have after it has thrown the ball. I've been meaning to get around to this, but I haven't done it yet. But it shouldn't be very much. And some of the very cool suggestions that have come up are magnets and using like a repulsive force to kind of bounce it back. Another cool one was eddy currents. So similar to how like those drop towers at the theme parks work, where they drop you down and then there's magnetic eddy currents that actually slow you down. But a big problem with this that someone named Ronnie suggested is that these elements weigh a lot. And whatever braking system we come up with, I really don't want it to come at the cost of increasing the weight of this moving part, because whatever benefit we have from the braking is then going to be offset by the amount of force that the hand motor is going to need to exert to accelerate this higher mass to be fast enough. So I really don't want to increase the speed of the ball, I don't want to increase the mass of this stuff. There is one very, very, very cool idea that I am seriously processing, which is to use, rather than normal springs, using constant force springs, which I actually have some of, but I don't know where I've moved them to. Yeah, somewhere. They're basically like a wrap of steel. It's like steel tape that's been like wrapped up into like a little bundle, and when you pull one end, it wants to wrap back around with the exact same force pretty much throughout its entire stroke. And I'm thinking that we can use constant force springs that are locked down onto the bottom of the hand element down here. They come up, and then they are stopped from moving too far down so they don't compress fully. There's a little like block point, and then when the hand goes up, it will smack into these constant force springs. They will remove the energy from the hand and then bring it back down again. Maybe, but that might require a bit of space. Yeah, there's a lot of cool options here, and I'm very, very, very open to different suggestions for how to break the hand. I think it'd be very, very handy to do that. However, I'm not relying on that being the case. I am of the opinion that this will work as it is right now, with with the motor breaking the hand rather than needing any other mechanical thing. So my plan right now is to move ahead with this as it is right now, and then if I want to make it even more compact in the future, then we can kind of play around with it a bit. We can experiment. But that's not a huge that's not a huge priority for me right now, so I'll get there when I get there. But if anyone has any good suggestions, I would love to hear them, because good suggestions are always good. All right. There's been a lot going on, as you can see. It's been a busy week. Now, we should have a stream next week, so hopefully a lot of these problems will be a little bit more straightforward next week. Hopefully I would have gotten to the bottom of them. Fingers crossed, we'll see. But there's one final thing that I want to see if anyone has any good ideas about. Because this is frustrating me, and I think there's a really good way to do it. And I'm sure that people have solved this problem before, but I'm not sure how to do it. And I like Nebby's suggestion. Just don't stop the hand, have it launch off with the ball. That would be funny, but not very sustainable. The hands are getting thrown around. So my question for you all is that I have been slowly building up my supply and my capabilities with electrical things. So I'm stocking up my electrical components so that I have a lot on hand, and I've also stocked up on some hookup wire, and I now have solid core hookup wire and the non-solid core, whatever it's called, where it's got like multiple threads on the inside. I've got all of this hookup wire, but I really hate these boxes. I have these in a pretty accessible spot for me. Hopefully, maybe you can see in this. This camera's all right. Just behind this box here, there's a nice open spot here, and I've got all of my hookup wire here. But these boxes are just kind of crap. Like, you have to pull. Basically, whenever I'm using these, I have to take the box over to me, take out as much as I want, trim it off, and then I put the box back where it was before. There has to be. Someone surely has come up with a better way to store these wires so that you can just like pull out a length that you want, and then like a cigar trimmer thing where you just like, and then it snaps off the wire at like the length that you want. Surely that's a thing. And like, I don't know, like this one's already ripped. Like, it's just crap. So if anyone has any good ideas for how to store hookup wire, it doesn't even need to be remotely similar to what I've described before, just something better than these boxes. Because I am like this close to spending way too much time making my own one. And I would prefer to spend that time doing other things. Yeah. Yeah, Alice says, I agree they're terrible, I just don't use it enough to care. I have been the same up until now. I am very keen to get more into doing electrical stuff. This is something that I've wanted to learn for a long time, but up until now, I have had no real strong need to. And for me, if I don't have a need to do something, then, like, if I just want to learn a thing, usually it doesn't happen because I just end up doing the things that I prioritize more instead. So it just doesn't get learned. But now, I'm starting to see the advantages of being good at electronics stuff. I'm starting to see the advantages that brings. And I am becoming more and more keen to get better and better at this. And even just last night, like when I was setting up all of this demo stuff, this solid core hookup wire was so good. Setting up this like rat's nest of wires where I have just like so much crap going on. Solid core wires and Wago connectors, like that is bomber. Definitely way more bomber than all of the DuPont connectors bullshit that I was doing before. So it's very, very big step up. Except for these boxes. But yeah, any suggestions? I'm all this. Yeah, check 3D print sites. I have had a bit of a look around, but they're all just like this, but printed. It's like, it's the same thing. Like, why are you bothering to print? I get that it's like a bit more durable than the cardboard, but like, yeah, it's basically the same. I really want that little like a chopping mechanism. Something where you can just like, and then the wire's cut. Yeah. I'm going to spend too much time on this. I know it already. Yep. All right, cool. Well, I hope you found that interesting. I know I kind of rambled a little bit, but that's just how the last week has been. A lot of like, I have a good thought about what I can do, and I try testing that, and then I realize how much that affects something else, and it's like, okay, cool, I need to test how this other system works, and then I got to test how, like, there's a lot of things being brought together, and I'm just wanting to make sure that I do it right, and that I'm being mindful of all of the other considerations as I'm moving forward through this, which I completely recognize can come off as fairly chaotic, but that's just the process, or my process at least. Yeah, Alice is saying you need like 8 pairs of side cutters. Oh, I mean, I'm pretty sure I bought these side cutters for like $3 or something, so that's not that bad. We'll see how we go. The space, I think, I'm really just fingers crossed that someone has a good suggestion. I'm going to give it like 2 weeks or so, and I'm just going to hope that someone sees this and makes a really cool one. Alice, you'll design one. Nice. About 20 centimeters wide would be perfect. Yeah, I'm keen. You can save me the effort. Yep. All right. That's enough rambling. Cool. I will put links in the description for all of the stuff related to this. I didn't have enough time at the beginning of the stream to fill them all in, but there'll be links for all the usual stuff in the description. Cool. All right. Well, yep. Thank you for joining me, and I will see you next week. So until then, have a good one.